Good afternoon. Good afternoon, everyone. This is welcome to the first live session. So, because of some technical issues, we were not able to record the session properly during the live session. So, I will just be recording it, re-recording it for the purpose of YouTube. So, just myself and about the course. So, welcome to the first session for the NPTEL course, a brief introduction to microsensors. The course code is NOC24 0009. This is the first live interactive session. The course instructor for this course is Professor Shantanu Talukdar, Assistant Professor, Department of Electrical Engineering and Computer Science, ISER Bhopal. Myself, Ahmed Ukale, a Prime Minister's Research Fellow at Department of Mechanical Engineering, IIT Tirupati. I'll be your mentor for this session. My sessions will be on Monday, 6 to 8 p.m. So today is the first session. So before we begin, we'll just I'll just switch to full screen mode. Okay, so now I hope I'm visible as well as the slides are also visible to you. I'll just pin myself here. Great. So yeah, so let's begin. Before we begin, we'll just before we begin, just giving you some important things. This is a live interaction session to boost your performance in the exams. This is not compulsory, but it is highly encouraged that you attend these sessions. It is request you to be respectful in the chat. Do not spam it, and in case of any doubts, just unmute yourself and ask the question. It's fine. We are here to have an interactive environment, not to just like make it a one-way session. If you want, it is you can discuss. You have to stick mostly to the assignments when we are actually solving the problems. In the end, you can even discuss your research or something else as well. You can ask the questions at the end of the chat, and the videos will be uploaded on YouTube in this channel. So I think I am clear about this. So yeah, let's go ahead with the session plan. So today I'll be having revising some important concepts. Then we'll be discussing a practice assignment 0. Then we'll discuss practice assignment 1, and then we'll have a question and answer session for you. So just giving you a course outline. This is a 4-week course. This is the first week. Here we are mainly talking about what is micro sensors, how are MEM sensors, and we are introducing them, what the applications are. In the following weeks we'll go into the fundamentals, their manufacturing, and case studies as well. So in this week we'll stick to the introduction part. So we first begin by revising the important concepts. So yeah, so what is a sensor? So it is very difficult to define what is a sensor per se, but International Electrotechnical Commission, that is a statutory body. Like you, for mechanical engineering, there is ASME, American Society of Mechanical Engineers. For electrical engineering, it is IEEE. So like, yeah, for like electrotechnical, so there is one more committee called Electrotechnical Commission. So as per them, sensor is a primary element in the measuring chain, which converts a variable signal that is usually non-electrical into electrical signal. So some of the like preliminary old age examples of sensors are pressure gauge as well as the thermometer. In a pressure gauge, the atmospheric pressure is measured by the change in mercury levels, and in the thermometer, the temperature is measured by the change in by the expansion of mercury due to temperature. But now coming to our topic, so we our lecture is mainly focused on microsensors. The topic is brief introduction to microsensors. So we need to know what scale we are talking at. So MEMS are basically the devices that are less than 1 mm and more than zero point 0.1 micrometers. So in that range we are talking. We are not going into the nanoscale. We are not going into the millimeter scale. So we are the devices, the sensing equipment. So the entire device may be bigger than 1 mm. So the compressor so the processor in your laptop or the mobile which you are using right now, that the entire device is more than 1 mm, but the feature size is obviously less than 1 mm. The feature size of a particular device, a particular uh, component of that entire assembly is in the micro scale. So that is why we call that as the micro electromechanical systems, MEMS, and that is the scale which we are talking about. So yeah, so why do we need to study MEMS? Why is this course important? So you can see the MEMS market is steadily increasing. It includes everything: the sensors, the RF MEMS, the microfluidics, the digital compasses, gyroscopes, microphones, etc. All the devices, the market is increasing. There is now, you can see from the last 6 years, the market is just increasing. It is not reducing at all. So the demand for workmen or the people in this industry is only going to increase and not going to reduce as of now. So it is very important career from your career perspective as well to have knowledge about MEMS. So just giving you some applications of MEMS. So one of the main applications of MEMS is biomems, which is in the biomedical domain. So you can see this is the device for microneedle. So there are many people have a typhania. So typhania is basically the fear of needles. So that fear of needles, the people with typhania are basically not given any vaccines, or they are very hesitant to take vaccines. So in you might have seen in the COVID-19 pandemic, which we had very recently, the vaccination was played a very important part. So in order to deliver vaccines to people like these, we use some devices called as microneedles. So basically, these are like a patch, like the band-aid which you use in your day-to-day life. These biomems are these microneedles come in a patches like your band-aid. You can just paste them over the person's skin, and they will dissolve themselves, or they might just puncture it so much in a painless manner and deliver all the drugs to the person without the person having to actually look at the needle or even have to having a pricking sensation from the needle, because it is very small. So the thickness of microneedles will be in 300 micrometers, which is basically negligible for a person's skin. So using these devices, the person who are fearful of needles can also be vaccinated, and it is also used for monitoring of babies as well. So if there is a babies who are also very fearful of needles, so in that case also we are these micro needles can be very useful. So then there is something called gas sensors. So gas sensors are basically used for measuring the nitrogen, oxygen, argon presence in a room, and also even in other setups as well. So these are basically used for find measuring the gases, and these are also MEMS based devices. Then there are motion sensors, the motion sensors which are basically used in many places right now. Basically, if you enter a in elevator, or even if you exit some airports or malls, you can see the doors opening automatically. So the sensors which are present there are motion sensors. Basically they have measured the airstream. So if when you walk through a area, you will disrupt the airflow, and you measuring that airflow, they measure the like they sense the motion. So those are called as the motion sensors. And then there are force sensors, which are basically they measure the force that is being applied there. These are very highly used devices, and this is the things which are being discussed mainly in this course. So with the next slide. So let's go to the next slide. So what is the fundamental in this lecture? So basically in this lecture, they are mainly focusing on scaling loss. So in first week, the content is mainly focused on scaling loss. So basically in scaling law, what we are doing is basically we are scaling it down. We are scaling from the millimeter scale and bringing it to the micrometer scale. So what is the major advantage of scaling it down? So basically, when you scale down, some laws that are laws of nature actually change. So if you actually look at microfluidics per se, compared to the normal fluid flow, in microfluidics, the mainly the flow is laminar in nature. It is not turbulent. So those are the things which actually happen at the micro scale. So that is something which we need, for which the scaling laws actually matter. In this case, just take an example of a cube. We scale it down. So we have a edge length of 10, and then we have a edge length of zero point 0.1. So the volume we have to multiply by the scaling factor, and then we get the actual volume. So you can see how the volume is changing after we scaling it down. So with that, the various other forces which are actually negligible at the macro scale come into play. So you will learn about those forces in the next weeks, following weeks. So just keep in mind that why we are scaling it. So we are scaling it because we need to harness some other forces which we are not able to harness at the macro scale. So we are using it for that reasons. So how a MEM sensor works. So coming to how a MEM sensor works, basically we have any external forces applied on it. Then there is a moving structure. So a cantilever or a membrane. That moving structure is deformed. So after that deformation, we measure that deformation, and from that deformation, we back calculate what is the external force that has been applied. So here it is a cantilever beam. So here force F is applied and we are measuring the deflection X. So what we do is we change the cantilever beam into a spring mass system, and using the governing equation F is equal to Kx, we determine the force that is applied. So we already know the stiffness. We calculate we already know the stiffness, we already know the deflection. So we just need to calculate the force applied. But so to calculate the stiffness per se, we need this equation. So this is the Euler-Bernoulli equation. From this we can calculate the stiffness of the material as well as how. So from the and from that stiffness we can calculate the force. But and to calculate to actually solve this equation, you need some boundary conditions. Basically you have this beam or membrane. You create a free body diagram, and you find out all the forces that are acting on the beam, and you break that those forces down, and you get a free body diagram. So and then from that you put the specific conditions, and then you get the you solve the equations accordingly. So we'll just start with the assignment 0, which is the non-graded assignment. So yeah, so the first question, assume we have a parallel plate capacitor with capacitance C. The charge stored in capacitor is Q. If the voltage across the capacitor is V, then V can be given by which of the equation? V is equal to Q by 2C square, or V is equal to C Q square, or V is equal to CQ, or V is equal to Q by C. So any question, any guesses? Yeah. So here we have a power source which is supplying potential V. So the negative terminal is connected to this upper plate. So the negative electrons are moving from one the terminal to Q. So that is charging it the capacitor positively, and the opposite plate is getting negatively charged, and that is how the capacitor is storing the current basically. So once the charges exceeds the capacitance value, so the dielectric medium between the two between this parallel plates will break down, and the capacitor will act as a short circuit. So the capacitor, the basic formula for capacitor is Q is equal to CV, or C is equal to Q by V. So from that equation you can get the value of V. So the value of V is D. So the answer to the question is D. V is equal to Q by C. So any doubt? Okay, so we move to the next question. So question two, assume an application of voltage V and in the same question. So the after the application of voltage V, the energy stored in the capacitor is J. Then the value of J is equal to CV square by 2, CV square, CV by 2 on CV. So anyone knows the answer? Okay. So what we do is at any instant t, we assume that the charge q is being transferred from one plate to another. So to move that charge q across the capacitance, we need to apply force. So the voltage applied q dash to c is you can give that q by that equation. And so to do that work, we need to apply that voltage on that charge. So we just integrate the voltage uh, to, over. We just integrate the equation over the entire charge Q, and then we get the uh, the energy is in the form of half Q square by C. So then we just put Q. We substitute the main equation Q is equal to CV, and that is what we get as J is equal to 1 by 2 CV square. So the answer is A, J is equal to 1 by 2 CV square or CV square by 2. So now we move to the third question. The third question is suppose a point charge Q is kept in free space. The magnitude of the electric field and electric potential are E and V. So basically, that is what we need to find from distance r at distance r from the point charge, and absolute permittivity of air is epsilon naught. Then choose the right options. So you need to these are your options. These are very few fundamental questions equations you actually need to know quite well. So I expect you to know this. So from your 12th or 11th standard physics. So any guesses about this answer? Okay. So the field at distance r away from the point charge can be given by this equation. So 1 by 4 pi epsilon q by r square. This is the very fundamental equation you can find out in your 12th standard physics books. And for electric potential, basically electric potential is the energy that is required to move the charge from point A to point B. So basically you get the initial charge at in first point and the charge at the final point. So here the charge you are just moving from the origin to B to R. So the origin is zero, considered zero. So your answer will be Q by R. So the answer for this is option A, E Q upon 4 pi epsilon naught R square, and V is equal to Q 4 pi epsilon naught R. So we move to the next question. So this is the question number 4 to 6. We have a common passage given here. So here we have a cantilever beam with length L and cross section area A. The left side of the beam is fixed into the wall. The beam is pulled by an axial force F such that the length of the beam increases by delta L. There is no bending or torsion that is in the beam. So this is a very important point. The material is having a Young's modulus Y. Now we have to answer the following questions. So the axial stress on the beam is given by FA, F, F by A, by the Young's modulus into area. So any cases. So basically, axial stress is that in one which is passing through the main axis. So there are two type of stress. There is axial stress and tangential stress. So the tangential stress is called as the shear stress, and the axial stress can be either compressive or uh, tensile in nature. So in this, since it's being pulled, it is a tensile stress. So yeah, so this is how it is. This is consider a rod with initial area, initial length L, and then it's being pulled. The force is applied in the center, that is in the axis of this body. So the force is given by force upon area. So what is the stress? Stress is basically when you are when you are pulling it apart, the molecules of the body are also are being pulled apart. So when they are being pulled apart, there is basically for every molecule there is attraction between them and repulsion, and they are in the equilibrium. So when the equilibrium is trying to be disrupted, there will be obviously there will be some opposite reaction, because as per Newton's law, there is for every action there is equal and opposite reaction. So in this case, when the body is being pulled, there's some internal forces are being developed um, inside the atoms or the molecules of the material. So that force that is being developed is called as the stress. So you may be confused by the formula of stress and pressure being the same, but the pressure is basically the external thing that is being applied, and stress is basically the internal thing. Although the formula might be the same, the conceptually these are two different things. So the answer is C, F by A. So now we have strain. Strain is basically the change in length upon original length. So whenever the body is being pulled, there will be a change in length. So to measure that change in length with respect to the initial length, we use the concept called strain. So the strain is delta L, L plus delta L by L, or L by delta L. So any questions about this? So yeah, strain is change in length upon original length. So that is delta L upon L. So the Young's modulus. So what is the Young's modulus? How will what will be our relation between Young's modulus, stress and strain? So what from this we have four options. Young's modulus is stress into strain. Young's modulus is stress upon strain. Young's modulus is strain upon stress. While Young's modulus is half strain upon strain into stress. So this is basically a stress strain curve. This is a stress strain curve which has the two in the x-axis there is the strain, and on the y-axis there is the stress applied. So that is the stress. So in up to the proportionality limit, the stress is proportional to strain. So in this within this limit, the relation between stress and strain is given by stress is equal to Young's modulus into strain, or here for this equation it will be Young's modulus is stress upon strain. So now coming to the seventh question, voltage V has been applied across a metal wire with electrical resistance R. Then the current is in this wire through this wire is V by R, VR, V square R, or R by V. So this is a very fundamental question. I expect everyone to know this. This is basically based on something which you have learned in your seventh or eighth grade, something called as Ohm's law. So here we have a circuit. Voltage is applied. So when the voltage is applied, there is a current flowing. So the current is flowing through the resistance R, and then you will have the relation V is equal to IR, or it can be this can be a Ohm's law triangle. So basically, what you are seeing, so if it is V, if you want it, it's IR. So if you want R, it will be V by R. So it is a very easy trick to remember everything. So the answer is A, V by R. Current is V by R. So coming to the eighth question, so we have two charges, Q and Q that are being kept at distance d, and the force between them is found to be F1. Then we increase the distance between the two charges to 2d. Then the force between them becomes F2. Then basically, what will be the relation between F1 by F2? So will F1 be 4 times F2? Will F1 be equal to F2? Will F1 be half? So F2 will be 2 F1, or will it be F1 equal to twice F2? So basically, here you can see that uh, when two charges are kept apart, so if they are like charges, they'll repel each other. If they are unlike charges, they'll attract each other through a force. When the force relation between them is given by this equation 1 by 4 pi epsilon naught q1 q2 upon r square. So here we have from this relation we can find that the force applied is inversely proportional to the distance. So if we are increasing the distance, uh, the force will be 1 by 4 times. So here it is f1 will be 4 times f2, or the answer of this will be 4. I hope there is no doubt till now. Now let's continue with the week one practice assignment, which is the non-graded assignment. So the first question is basically mark the correct workflow for MEMS force sensor. So we have just revised this. So we have to find out what is the correct options among these. So in the first option, it is external force, the moving structure, deflection of moving structure, calculate applied force, measuring deflection. The second option says first external force, we calculate the applied force and deflection of moving structure, then the moving structure and the measuring of deflection. So uh, then the third option is external force, moving structure, deflection of moving structure, measuring deflection and calculating the applied force. And the third one, in the last option, it is the measuring. It's D actually. Sorry for the typo. Measure moving structure, measuring deflection, external force, deflection of the moving structure, and calculating the applied force. So I think this is fairly well known to you, because the thing is we need to measure the external force. So the external force will always be applied. So and we have to find calculate the applied force. So in the first in all the options, our main thing is to calculate the force through by calculating the deflection. So the applied force, calculating the applied force should be at the end of our measuring chain. So from this all these options you can clearly find out that the third option, that is option C, we can see that the chain starts with the external force and ends with the calculation of applied force. So that is how the chain will be. So even if in all these cases you just need to look at the input and output of the sensor. So from the basic definition of sensor, we know that it is from one form of converting the input from one form to another. So in this only, and we are measuring what is to be measured. So here we are measuring the force. So there is no by measuring the deflection, so the entire thing that has been calculated is the applied force. So the answer is option C. So now coming to the second question, this is a numerical type question, this is not an MCQ question. What is the critical length of a glass cube having density 2500 kilograms per meter cube in to float in a fluid having surface tension 27.56 millinewton per meter? Um, Neglect the buoyancy force acting on the block and take G is equal to 9.8 meter per second square. So this is a fairly simple question. So basically, what is the critical length? Critical length is basically from here, and from this diagram you can see that when a body is immersed in water, there is one force, that is the weight of the body, that is acting downward, and then there is a surface tension force, that is the force of the liquid that is going upward. So for that to happen, uh, that the surface tension force, so for the body to actually float in the water, the both the force have to be balanced. So there is only a certain length scale at which these forces can be balanced. If the body is too large, it will direct, the weight of the body will be too high to not being able to overcome the surface tension force, and then the body will sink. So here the condition to find the critical length is the surface tension force should be greater than the weight of the block. So surface tension force is given by 4 tau L, and if that is greater than rho L cube into G, so that is the density into volume into gravity. So from that you can get the critical length as 2.12 millimeters. So then we have our third question. Third question is basically we have a block hanging vertically downward by parallel beams of weight W, length L, and depth H. The beam material is elastic in nature, has the elasticity constant E. So what will be the equivalent spring constant? So you can see the diagram here. The options are WHE upon L, WHE upon 2L, 2L, 2 WHE upon L, and WHE into upon 4L. So what do you think will be the answer? So as we have learned earlier, we have to convert this entire setup into a spring mass setup, into a spring mass system. So here is the spring mass system. Basically, in the spring mass system, you have we have converted both the beams into springs and the block into a mass. So since the two springs are now connected in parallel, their spring constant. So basically, this is the formula for springs in parallel. So the total spring constant is twice the individual spring constant. And from the equation, we know that the spring constant of a single spring is WHE upon L. So here the total spring constant is 2 WHE upon L. So that's the answer, 2 WHE upon L. So now, yeah, this is a uh, question which makes you think rather than use basic formulas. So in this figure below, we have a matchstick, matchbox, basically matchstick with length of 50 mm and a cross section area of 4 mm. Assume that each matchstick needs 1 mm square of surface coating for ignition. Consider the matchbox is of size of 50 mm by 30 mm by 4 mm. Then is there enough ignitable area for the matchstick in this scenario? So can we find this? So to find this, basically we need to know, we don't know anything about this. We don't know how much matchsticks are there in this box, um, and how much area is there in this for ignition. So we actually have to assume looking at this figure. So from looking at this figure, we know that the ignitable area is the width into height. So width is 30 mm and the height is 4 mm. So we are considering only one surface is being coated like it is shown in the area, and we know the volume of one matchstick. So here we know that the number of matchstick is basically can be the volume of matchbox upon volume of single matchstick. Although there will be air in the matchbox, but we are considering that there is no air in this scenario. So we find the volume of matchbox, which is length into breadth into height, and for the volume of a single matchstick, basically it is we are considering it as a cylinder. So it should be pi r square L. But anyway, we have the cross section area. So cross section area into L. So we get the total number of matchsticks is 30 matches, and then to find the number of matches that can be lit, we divide the coated area by the area that is required to light one matchstick. So that is the coated area is 30 into 4, and 1 mm square is the area required to um, light ignite a matchstick. So in total, 120 matchsticks can be lit from the coated area. So that is way more than the number of matches we have in the state. So from this, we get that there is more than enough area for all matchstick to be lit. So now coming to the last question. Consider a cantilever beam of length L, B, and depth H made of Young's modulus Y. If the fundamental natural frequency is after scaling through width is alpha into B and depth is beta into H. If the natural frequency changes from F1 to F2, calculate the ratio of this frequency F1 by F2 if the value of alpha and beta are 10 raised to minus 3 and 10 raised to minus 4 respectively. You can use the frequency 1 by 2 pi root over k by m, where k is the stiffness and m is the effective mass of the beam. Again, m is equal to cmb, where c is the constant and m is the actual mass of the beam. If you can consider only transverse vibration. So we just need to find how the natural frequency is the frequency at which the resonance occurs. So basically, when if basically the frequency of vibration and the natural frequency match, there will be resonance occurring in that body. So for this, the formula is 1 by 2 pi root over k pi m, and from that we can find the actual mass of the from that we can find the resonance frequency. So here, since we have to only find the ratio of the um, to a resonance frequency, we use the formula and we directly divide by them by each other. So we know that 1 by 2 pi will get cancelled. We know that m is constant for that beam, so will get constant. So only thing remains is k1 and k2, that is initial spring constant and the final spring constant after scaling. So then we substitute it. We can cut all the other constants, and we only are left with the only the scaling factor. And from that we find that the um, uh, final ratio will be 10 raised to 4. So with this we have ended the questions from practice assignment 1 and practice assignment 2. If you have any questions, you can please let me know. Does anyone have any questions? In case you are watching it on YouTube, you can even put your questions in the comment section of the YouTube video, and the PPT will also be embedded. The drive link for the PPT will also be embedded in the YouTube video. Then, since it's a YouTube video, I don't think anybody can actually give the questions in the real time. So actually, we'll just end the meeting. I would like to thank you for giving your time for this session, and I would see you next week. Then, since it's a YouTube video, I don't think anybody can actually give the questions in the real time. So actually, we'll just end the meeting. I would like to thank you for giving your time for this session, and I would see you next week.